class. Remember, there's a topic for every week, and we did Introduction to Sage, then we learned Python, then we learned Python, and making code fast, then we learned how to write LaTeX documents. Last week we did symbolic calculus. This week we're going to do linear algebra. We won't be doing numerical linear algebra this week, but exact linear algebra, which is very much like what you have in Math 308. Then we'll talk about statistics next week, number theory and cryptography the week after, graph theory and combinatorics, and numerical computation, which will involve some numerical linear algebra. Okay, any questions before we get going today? Okay, so first, as usual, there's a new homework available, and it's about linear algebra. There are 6 problems, and you can look at all of them right now, and they're just problems. Let's see. Oh, Jonathan Lee, where are you at? He helped make these problems, so we'll see. His goal is to make it so that they were more well-defined and clearer, so you'll be the judge of that. So we'll see if he improved things at all, okay? Because I think that last week, maybe the problems were sometimes unclear. Yeah, so hopefully they'll be clearer this time around. Maybe they'll be ridiculously clear. No, but they should be definitely clearer. Okay, so regarding linear algebra, I'm going to show you, so now we're getting going. So there are a couple of references that are worth looking at. One is this quick ref. And here's what it looks like. It's a nice little reference card that you can print out and keep under your pillow. So, I mean, just to give you a little sense, actually, I should tell you what kind of the background and history is here. So, when I started using Sage, there was no linear algebra at all because there was nothing. I had used, okay, so I should go way back. So, when I started doing mathematical programming in the 1990s, when I was a PhD student, so I needed to do linear algebra, like we do in Math 308, where you have a matrix whose entries are rational numbers, or maybe elements of a finite field or something like that. Not numerical linear algebra, but algebraic type linear algebra, where you don't do any floating point round off or anything like that. This is the sort of thing that I cared a lot about. It comes up a lot in coding theory, in cryptography, in number theory, etc. It does not come up so much in, say, video games or applied mathematics, where you do lots of stuff with floating point matrices. And so the software available for exact linear algebra, which I think I'll just call linear algebra mostly, was not so well developed. And so there was one library called Lydia, an enormous C++ templated library, and it would take like an hour to build from source. You would choose to work with matrices over a couple of different rings and fields, and then it would compile all the algorithms for all of these sort of permutations of fields that you might use. And then after maybe an hour of waiting, your code would be compiled and you could run it. It's very frustrating. But at least if you recompiled with the same options, it would be fast. So I used that for quite a while. And then I also wrote a lot of my own linear algebra in C++. And I wrote a bunch of like PhD theses and papers about linear algebra and how to make it fast. It's very, very subtle. Just to give you a little tiny taste of some of the subtleties. Well, one of the homework problems you'll see asks to compute the determinant of a matrix, to write a little function to compute the determinant using expansion by cofactors. And as you can see, that when you implement it, it's insanely slow to do that. It's at least n factorial arithmetic operations just to compute the determinant of an n by n matrix. But there are much, much, much faster ways of doing these sorts of things. So you can reduce computing determinants to computing echelon forms, where you keep track of all the numbers that you're dividing by, and then you take the product of the entries down the diagonal. And that's dramatically faster. But then you can reduce computing echelon forms to matrix multiplication via some very, very tricky algorithms. Yes?
So the idea is like, you know, the determinant of the elementary matrices.
Exactly, you just multiply all those together. So that's massively faster than expansion by cofactors. There's a million like little subtleties like this. To give you another example, one of the fastest ways to multiply, so a finite field is like numbers modulo p. And this again is very important in cryptography applications and coding theory. So you have two matrices with entries modulo a single prime number p, and you want to multiply one by the other. So it turns out right now the fastest way to do that usually is you divide the matrices up into little submatrices and you multiply the smaller matrices. So that's kind of clever. But why is that useful? So you keep subdividing until your matrices get down to maybe 64 by 64 or something like that. And then when you get small matrices, you can encode multiplying two small matrices over a finite field by turning them into floating point matrices, then multiplying the floating point matrices, and then hoping and making sure that nothing overflows. And because the matrices are small, nothing will overflow, and then you convert back from floating point back to normal. And why should that be fast? Well, just because multiplying matrices with floating point entries is super important in things like video games and numerical simulations and so on. So even if you're doing work with integers, rational numbers, or elements of a finite field, you often want to do clever tricks to turn the problem into something involving floating point numbers, and then turn it back. And you kind of build up basic building blocks like that. In any case, there's a lot of stuff like this. Also, in the late 90s, there was a kind of general belief that this algorithm, so for linear algebra, how many steps does it take roughly to multiply two n by n matrices, to multiply them one by the other? Like, what's the big O complexity of just the most straightforward matrix multiplication algorithm? Yeah, exactly. It's O of n cubed. Because you take, so to multiply two matrices, you take like the first row and the first column and you multiply them, and that takes n steps, because you do n multiplies and some additions with those. It takes big O of n steps. And how many entries are in an n by n matrix? There's n squared. So you're doing n squared times n steps. That's big O of n cubed. It turns out that if you decompose the matrix into like 4 submatrices and multiply those, well, that would be just as much work if you multiply in the most straightforward way. But there's a clever idea of Strawson that lets you multiply using 7 multiplies and a bunch of additions. So instead of doing 8 multiplies for a 2 by 2 matrix, you can do it in 7. And that ends up, after you work out the details, giving you an algorithm for multiplying two n by n matrices that instead of being big O of n cubed is big O of n to the log base 2 of 7, which is better than 3. It's substantially better than 3. But is it really better than 3? So in the 90s, people kind of thought it might never actually be better in practice, that you could always just do it better by directly doing O of n cubed and implementing it well. But then people started getting really clever at implementing the Strawson multiplication efficiently, by people I mean Alan Steele, this one grad student in University of Sydney in Australia. He just got really, really, really good at implementing Strawson and ended up beating what everybody was doing with the normal O of n cubed multiplication and showing that it was really practical in practice. So there's a lot of like subtle stuff in exact linear algebra that just takes quite a bit of work to develop and can be extremely surprising. I mean, just to give you a little tiny glimmer of another thing. So we talked about computing determinants a minute ago. So a very fast approach to computing determinants turns out to be the following. So you have a big integer matrix and you want its determinant. What you do is you take a random vector v, just any random vector you want, and you solve ax equal to v. Somehow. Let's say you just have some magic black box that will solve ax equal to v. Then you look at the solution x, and it will be some vector with lots of big rational entries. To make this extremely concrete, let me just do this. So you'll see how to actually use Sage to do something. So I'll make a random matrix with integer entries. It'll be a 10 by 10 matrix, and the entries will be between 0 and 1. Oopsie. This makes the entries between 0 and 1. Actually, make it a little bit bigger. Make it 100 by 100. Okay. If I try to print it out, it'll just say it's a 100 by 100 matrix. Let's print out just the first row. Okay, so I just showed you how to make a matrix. There's also a command matrix, which I'll talk about more in a second. This row has a lot of zeros in it. So that's kind of boring. Oh, the way random matrix works is it gives you a number between 0 and 1 not inclusive, just like the range command in Python. So it just chose a bunch of randoms that are all 0. So let me make this 2. Looks like Alto is about to fix it for me. Okay, so now we have a random matrix with zeros and ones. And it's 100 by 100. And now let's make a random vector. Hey, yep. And it'll have 100 and actually over Z, 100 entries, and the entries will be between 0 and 2. Or 1, sorry. Okay, so there's our random vector. And then we can do a.solve right v. Any guesses how long this should take? So if you think it will take 1 second, raise your hand. If you think it'll take like 10 seconds, raise your hand. Okay. If you think it's going to be blazingly fast, raise your hand. Come on, more confidence in Sage. No? All right, well, let's see. I would say that's pretty blazingly fast. 0.08 seconds to solve. And you're probably not impressed that it solved that quickly until you see what the answer looks like. But you will in a second. But the way it actually solved right there was it computed a solution modulo some prime number p using floating point linear algebra and all kinds of stuff. It then took that solution and then wrote down another problem mod p, a different problem, and then used that to get a solution mod p squared, and then used that to get a solution mod p cubed. And it iterated that process and got a solution mod some big power p. And in parallel with doing that, it also does it mod a couple of other primes, puts them all together using the Chinese remainder theorem, and then it gets a solution. And also something called rational reconstruction. Let's see what the solution looks like. This is the first entry of the 100 entries in the solution. See? It's that big rational number. If we were to print out the solution, the string would have 10,000. That's not really so big. Doesn't sound very impressive, 10,000. I'll just print it out. Okay, so there. It's a big number, okay? Each entry, it's a vector, each entry having about 100 digits. 50 in the numerator, 50 in the denominator. Okay, and you have a question?
So that solves A equals B?
Yep. So what I was talking about determinants, and suddenly I just shifted topics and started talking about solving AX equal to V. But do you guys remember Cramer's rule, that really hideously bad way to try to solve a system? Right? You know what I'm talking about? Where you have like the solution X, you can write down your solution X as some determinant divided by some other determinant. Like every entry is some determinant of a minor divided by the determinant of your matrix. In the denominator of Cramer's rule is the determinant of the matrix that's on the left-hand side of your system. And so let's just look at the denominator of the first entry in this vector X. I think denom works. Nope. Maybe dot denom. Okay, there's the denominator. Now let's compute the determinant of this matrix. There should be a relationship because of Cramer's rule. I think that the determinant is probably twice that denominator, or minus two times it. See? So a very fast way to compute a determinant, instead of computing this reduced row echelon form, what you do is you solve AX equal to V, take the denominator of your random sort of vector X that you got this way, and then it's very close to the determinant, and with a little theory, you can determine what the quotient of the two numbers is. So, I'm just saying, there's a lot of little, I wrote a paper about exactly that at one point, and other things. There's a lot of like little subtleties like that. Okay, so in the late 90s, I started working on Magma, which is this computer algebra system in Sydney, and it, like, across the board, its exact linear algebra, almost in every context imaginable, was just like orders of magnitude better than all other software in the world. I kid you not. It was just like, I mean, there were a few like maybe fast libraries that people had written for their theses, but Magma, it was just getting applied to lots of problems, and their like key trick was super fast exact linear algebra. It just beat everything, but it was also completely closed source. Like all the linear algebra was written in C and not available outside of, well, it's compiled in C. So I used it for a couple of years and built up a lot of my research functionality for computing with modular forms and elliptic curves and so on top of Magma's code. And then in 2004, I switched over and started Sage, and it had to start basically from scratch with the linear algebra in Sage. There was a library called Linbox, written in C++ that had come along in the meantime, and it's still around, and Sage uses it. And if you want to learn to not like C++, I strongly recommend you look at the source code of this. I mean, my God. It's so painful because it's just like incredible, like nested levels of templating, and it's just like, and then look at the error messages you get whenever you mess up. It's crazy, but it is actually really good in that the things that, so they wrote a lot of papers about exact linear algebra algorithms. They would often implement their code in Linbox, and then they would run a benchmark and be like, hey, look, we're the fastest in the world, look. And they would you'd find code in here that had only been run for one benchmark in a paper. For example, one closely related library we used called IML by some of the same people, it had super fast code for solving AX equal to V, and it would give you an answer with possibly thousands of digits in the answer, but it had no capability of inputting a matrix whose entries were bigger than 32-bit integers. It was just really ridiculous. Like, you couldn't put arbitrary precision integers in, because they only used it for benchmarking, as it's called, benchmarketing. In any case, this beautiful open source library with very painful C++ code is used a lot in Sage. And then in addition to that, we wrote a lot of really, really painful code to implement just lots and lots of exact linear algebra algorithms. So I wrote a bunch, and then a bunch of grad students sort of took over in 2006, and it kind of got developed over many years. Also, there's a library called Flint, flintlib.org, which is a fast library for number theory. And it's a pure C library, and it has a lot of very highly optimized code for exact linear algebra. You can use it in anything that can use C code, which is pretty much anything out there. So this is good to know about. This was written by some Sage developers and other people many years after we started, in order to make it so that instead of implementing algorithms directly in Sage, you could implement them somewhere else, have them much more widely available, and then use them from Sage. So a lot of Sage code uses Flint under the hood. Okay, so that's the history. Oh, and one other key point about the history, and this is, I'll put this in the bullet point. This is a summary of what I'm talking about. So there's a bunch of code in Sage that was written by me, grad students, the authors of these like professionals at exact linear algebra, and then a bunch of kind of undergrad teachers. So a bunch of people who want to write books on linear algebra and use Sage, or they're teaching classes like Math 308 using Sage, and they needed certain functionality to be there, and it just wasn't there. And so they would write it. And you can tell the sort of design goals are a little bit different. For example, and we were just looking at this a few minutes ago, there's a function in Sage called isSimilar. Given two matrices, it'll tell you whether or not they're similar. And I don't know if you guys remember what that means. Does anybody remember what it means for matrices to be similar? Uh-oh. Okay, I need to, not good. Damn, I hate these extensions. You have to actually disable it. My wife is apparently about to get a job offer. Okay. From the iSchool here. So teachers wrote a bunch of functionality, and it's not necessarily aimed at research or speed. So like the isSimilar function, given two matrices, you can tell whether you can get from one to the other by a change of basis, by conjugating. By basically changing bases, can you get to the other matrix? So it's a basic piece of functionality. I was just looking at the code, and the way it works is it checks if they have the same characteristic polynomial. If they don't, it says they're not similar. If they do, it computes the Jordan canonical form of the two matrices, which you may or may not know about, but it's like a good piece of functionality to have, this Jordan canonical form, but it can be very slow to compute. And it was implemented by people purely for teaching purposes, so it's really, really slow. So if you use this isSimilar function, you might find it shockingly slow. because like researchers never really needed it and teachers did. So you have to watch out because there can be functionality in Sage where there's one function that looks really similar to another function, and that one function is orders of magnitude slower than the best code in the world, whereas the other one is the best code in the world, and they're right next to each other. And you might not know the difference unless you kind of understand the underlying algorithms. So that's a warning. Hopefully this code will all be replaced by fast code that does exactly the same thing over time, but I mean, it's a general caveat. Okay, so next, what do you want to know about? Let's see. So I just showed you. Okay, two basic things to look at: matrix question mark and vector question mark. Matrix. So here's another thing. So so in Magma, the way you make a matrix is you make the space of all. This should seem very mathematical. If you want to make a matrix with entries in the rational numbers, you would make the space of all, say, 2x3 matrices with rational entries. Right? Somehow it's like a vector space itself with 2x3 matrices. And then you would create inside of it, using something like this. So it's very, very explicit, your matrix. And I thought that was kind of a little bit too painful. So I wrote a command matrix where you can just give it a bunch of entries and it will figure out what sort of, you don't need to know that there's this cute thing at all. It will just figure out where to put the entries and what size the matrix should be and do all that automatically. And this is very explicit. There's like no ambiguity in what's going to happen here. It makes the space of matrices over Q. It makes the matrix, if you give it anything that's slightly off, it's just going to give you an error. Whereas when you use matrix, it tries to sort of automatically figure out, based on what you give it as input, what the matrix is supposed to be. Like you could give it maybe a function that takes two entries, two inputs, and then it will, and a size, and it would run through and construct a matrix whose ij entry is given by some function. And so because this is very powerful and nice to use, it can also be a little bit subtly ambiguous. And so you need to maybe look at the documentation. But it's, of course, very useful. So if I want to make that above matrix using the matrix command, I'll just do this. And it'll just figure out, oh, all the entries are supposed to be in the rational numbers, and so on. It just does all that automatically. So, of course, this is pretty easy to use. And you can just put kind of anything in here. You can put symbolic things like pi, whatever, and it'll just figure out where they're supposed to go. Yes?
Is there a way to have it separated as the columns?
Actually, no, but you can do dot transpose.
Oh.
So you can do that. But I think there isn't, I might be wrong. When I wrote it, there was definitely no option to the matrix command that would interpret them as columns. But, well, possible there is. I don't think so, though. One thing about, I don't see anything. Hey, that's me. Why does it say double question mark? What am I, the Riddler? Okay, so, yeah. And vector is similar. Some things to know about matrices and vectors. So a matrix, it's a rectangular array of numbers. They all have to live in the same ring or field in the sense of Sage. So they all have the same inherent ring. They're all rational numbers, they're all integers, or they're all symbolic. They all have to be the same sort of thing. This is very different than like a list in Python, where each entry could be completely different than the other ones. Also, they have to be numbers. You can't make a matrix where an entry is a list, or an entry is a picture or something. Each entry in a matrix must be a number. Okay? Also, matrices in Sage are 2x2 rectangular arrays of numbers. They're not like, we'll learn about NumPy at the end of the class. NumPy has a notion of n-dimensional arrays, where they can be like 3 or 4 dimensional, where you can have like rows and columns, but you have a dimension in the other direction that gives you something about color or something else. So, or 3-dimensional meshes. That's not what you get here. These are very mathematically oriented objects. Also, when you use asterisks to multiply two matrices, it really is matrix multiplication in the mathematical sense. It doesn't just multiply the elements pairwise, which confused me to no end when I compared. I was trying to benchmark Sage versus NumPy before, and in NumPy, you can make arrays, 2 by 2, or you can make two-dimensional arrays, and when you use asterisks, it just multiplies sort of term-wise, like just corresponding entries of the array are multiplied. And that's, of course, really fast to do. So whereas multiplying using matrix multiplication is very slow. Okay, what else do I want to tell you about? Wow, there's a lot of documentation here. Geez, what the hell? There's too much. I'm going to delete the output. Okay, so here's an example just of making a matrix. You can specify explicitly the number of rows and columns, and you can put the entries anywhere. Sometimes it's really tedious to type a list of lists, so you can alternatively specify this matrix as follows. If you give the number of rows and columns, you don't have to give each of the, oh no. By the way, I finally made everything related to synchronization and the database sufficiently stable that I get to work on fixing Sage worksheet rendering, which is what I spent all day yesterday on, which is basically turning the underlying Sage worksheet into what you see, which is clearly broken, as has just been demonstrated. I'm going to switch to this. So if you just give an array like this, it knows that it has to be a 2 by 3 matrix, so you don't have to explicitly give a list of lists. This can save you a lot of time when you're typing, if you ever have to type in a matrix. And then show, nicely typesets the matrix. And similar to vectors, you can see a nice vector like this. By the way, vectors are, they normally print as row vectors, just because that's more convenient. But vectors in Sage are neither row nor column vectors. They're both. They're not like one or the other, they're just either one. If you have a matrix, you can multiply a vector by it on either the left or right, if it makes sense, and it will just work in the appropriate way. If you explicitly really want something to be a row vector or a column vector and to print that way, just make a 1 by n or an n by 1 matrix. And that will do what you need. So here's an example of what I just said. I'm multiplying the vector on the right by a, but you could just as easily do v times a dot transpose. And you don't have to explicitly transpose v at all. I hadn't defined v, sorry. Because that was from before. But look, see. There's echelon form. I'll just show that. There you are. So notice it keeps everything exact and does the whole thing. There's a lot of functions on a matrix. So obviously there's things like determinant, characteristic polynomial, row space, column space. These are already very interesting because so Sage goes a whole level or two beyond just the idea of working with matrices to working with vector spaces. So given a matrix, you can say, hey, give me the row space. And then given another matrix, you can say, hey, give me its row space. And then you can say, give me the intersection of those two subspaces. Or give me the sum of those two subspaces. Or given a vector, is it in one of those subspaces? You can do all kinds of things like that. And you can even do this sort of thing over the integers instead of the rationals, which is pretty subtle. In any case, let me show you an example. So if you want to try this yourself, you can set a random seed. If you do that, then all the random numbers will be sort of well-defined based on that choice of seed. So here's a matrix. The default for a random matrix over Q, it has entries where the numerator and denominator are between, well, basically 0 and 2. They're all either, those are the entries you get, somewhat randomly chosen. It's kind of silly, but that's what you get. So let's just take a look at what happens when you do a.tab. You can see a large list of functions. There's over 200 things listed here. Some are aliases, det and determinant are identical. Some are kind of obviously really easy to implement, like diagonal. But others are much deeper, like eigen spaces right. Okay, let's try that one. So what this does is, it's kind of hard to see. I'll assign it to a variable and then tell you about it. I'll just give you 0. E. So there are 5 eigenspaces. A is a 5 by 5 matrix. What this does is it computes the characteristic polynomial of this matrix, finds all the roots, and then for each root it computes the corresponding eigenspace. And this will work in a lot of generality. It works over, well, let's see. Just to give you a sense that this is pretty subtle, let's compute the characteristic polynomial. Char-poly. Oops, not a.char-poly dot factor. So it's an irreducible polynomial of degree 5. There's annoying denominators, etc. And there's no like simple formula for the roots of this polynomial, but it still, via pretty tricky stuff, computes exactly all 5 roots and exactly finds the eigenspaces and gives you a basis for each one. Yep.
So when like if you have a polynomial, it's like you want it's like with respect to over Q or over Z or whatever, and then that will determine how factor functions.
Yes, yeah, that's correct. So if I do f equals a.char-poly, and then do parent of f, it's a univariate polynomial over the rational field. And you can also say f dot, I think, base ring, and it tells you that the base ring is the rational field. And then when you do factor, it factors it over the rationals, but you could do f dot change ring, change the base ring to be the double precision real numbers, and then call factor, and that's the factorization over the double precision real numbers. So an idea like a function like factor is only meaningful relative to a choice of ring or field. Does anyone here, so just in case you don't know what a ring or a field is, does anyone not know what a ring or a field is when I say that? Okay. Wow. So I get to tell you what a ring or field is. So, remember fractions, all the numbers a over b. If you add together 2 of them, you get a fraction again. If you multiply 2 fractions, you get a fraction. If you have a non-zero fraction, you can divide and you get another fraction. So basically, you can like live in a whole world of just doing arithmetic with fractions. That's an example of a field. It's a collection of numbers where you can kind of do addition, multiplication, division without leaving that collection of numbers. Another example is real numbers. You can add and multiply real numbers. You never accidentally see a complex number just pop up. When you do addition and multiplication, you stay in the real numbers. Same is true of complex numbers. An example that isn't like this is take all polynomials with rational coefficients. You can add them and multiply them, but what if you divide them? You suddenly get something that's not a polynomial anymore. So that's not a field. A field is like a collection of numbers for which you can add, multiply, and divide, and you stay within that collection of numbers. A ring, on the other hand, you don't have to be able to divide. You just have to add and multiply and stay within there. Some examples of fields are the rational numbers, the real numbers, the complex numbers, all rational functions. So take polynomials divided by other polynomials. All rational functions, that's an example of a field. Another example of a field is take all complex numbers, a plus bi, where a and b are rational. So that's called the Gaussian numbers. I don't know. Well, if you take 2 numbers of the form a plus bi and add them, you get something again of that form. If you multiply them, you get something of that form because you can kind of simplify. And you can also divide by rationalizing the denominator. So that's another example. When I talk about a field, I just mean a collection of numbers where you can add, multiply, and divide. Okay, now you know what a field is. And a ring is just the same thing, but you're not guaranteed to be able to divide. That's it. And a group is a collection of numbers where you can multiply and divide, but you don't necessarily get to add. And there's a 1 in inverses. Okay, so if I put CC here, I'll get a different answer. Over the complexes, you get every polynomial factors is a product of linears, which is the fundamental theorem of algebra. Despite the proof being in complex analysis. Okay, so I want to stop in like 1 minute, but let me just show you one more thing. Determinant. I'm just going to compute a few other things with this matrix. So there's the determinant. I did char poly dot, say, row space. This is going to be pretty boring. It's just the full. But this is an example of a vector space. You can also do QQ, say, 3. You get the vector space of dimension 3 over the rational field. You can ask for the span of vectors. So I'll make the vector 1, 2, 3, and the vector 4, 5, 6, and the vector 7, 8, 9, and just ask for the span. Oops. So you might remember from Math 308 that given a bunch of vectors, you could consider their span. But in Sage, it's just a command. Span, probably not in your graphing calculator, there's a command called span, but in Sage there is. And you just give it a bunch of vectors, and it gives you back the vector space that they span. And the vector space is represented as, well, in this case, given by echelon basis matrix. This is a little subtle. This is the span. This is actually not a vector space. It's a free module over Z. Probably a lot of you haven't heard of what a module is. So who knows what a vector space is? Pretty much everybody. It's a bunch of vectors that satisfy some funny conditions. A module is the same thing, except in a vector space there was a field there. There was usually the real numbers or the rational numbers or something. A module is exactly the same axioms, except you replace the field by a ring. Something where you're not allowed necessarily to divide. So an example is polynomials could be the thing that you have a module over. The module of vectors over a polynomial ring. Or in this case, over Z. So if you want to be explicit and say, I want the span of these vectors over Q, you have to do that. And now that gives you a vector space rather than a module. But again, a module is, it's exactly the same as a vector space, but instead of a field, you have a ring. Like, you do everything just like in Math 308. Just imagine Math 308 if you weren't allowed to divide. And that's modules. Like when you do Gauss elimination, you're never allowed to divide. And so you can't, you can't make the first entry in each you can't make the first non-zero entry in each row 1 anymore. So things get a little more subtle. Right, so I've shown you quite a bit, most of what you need to get a lot of your homework done. So start looking at your homework right now.